Regardless of the structural form used, which materials are used, bridges will inevitably experience degradation sooner or later. Main factors affecting degradation characteristics and degree include structural form, building materials, construction quality, atmospheric environment, natural disasters, traffic load effects, scouring, etc. Therefore, regular inspections and evaluations of the bridge are required. Facilitates maintenance strategy formulation for managers. In this lesson, let us now learn the bridge technical condition assessment process. Bridge technical condition evaluation. Evaluated according to the Highway Bridge Technical Condition Evaluation Standard. Adopt a method combining hierarchical comprehensive evaluation with the 5-category bridge single-item control indicators. Rate the bridge as Class 5. The classification limits for bridge technical condition ratings are shown in Table 4.1.5. Single control indicators for Class 5 bridges have highest priority. If the bridge meets any of the single control indicators for Class 5 bridges, then the entire bridge is directly rated as Class 5 dangerous bridge. Single control indicators for Class 5 bridges are detailed in Standard Entry 4.3.1. If the superstructure has the phenomena of beam lowering, beam slab fracture, etc., the bridge can be directly rated as a Class 5 bridge. If it is found that there is no single control indicator of Category 5 bridges in the bridge during the inspection, then a hierarchical comprehensive assessment of the bridge can be conducted. First, bridge component breakdown. The bridge consists of the superstructure, substructure, and bridge deck system. Weight values for each location can be found in Section 4.2.5. The 3 major components consist of different parts. Components and weights vary for different bridge types. Detailed in Tables 4.2.1 to 4.2.4. Caution: component weights sum to 1 for each location in the table. However, not all bridges contain all parts. When a bridge lacks certain parts, allocate weights of missing components to other components. For example, the superstructure of a beam bridge includes superstructure bearing components, superstructure general component, bearing. If a certain bridge has no superstructure general component, it is necessary to allocate the weight 0.18 of superstructure general components. Allocate to the superstructure bearing components and bearings. Each bridge consists of parts composed of varying numbers of components. For example, a certain beam bridge consists of 2-span precast T-beams. Each span has 5 pieces of T-beams. The superstructure bearing components of this bridge consists of 10 components, 10 tons beams. Component division and naming for different bridge types are detailed in Highway Bridge Technical Condition Evaluation Guide. 2. Inspection and evaluation process. Before bridge inspection, name and divide the whole bridge components. On-site methods combine visual inspection with instruments. Inspect and record defects for each component. Potential defects in different bridge types and locations. See entries 4 to 10 for details. Standards assign different scales for various defects. Each scale has corresponding qualitative and quantitative descriptions. Maximum scales vary for different defects, such as honeycomb. The maximum scale for pitting is 3 degrees. The maximum scale of spalling and corner break-off is 4 degrees. On-site inspection personnel can adjust based on defect conditions. Determine the scale of the defect. Located and maintain proper recording. Hierarchical comprehensive assessment first follows each component inspection result. Conduct component scoring. Then, calculate the component score corresponding to the component based on the quantity and score of the component. Then, the components of the whole bridge are converted into the scores of each component according to the corresponding weights. The scores of the three major components are obtained by summing the scores of their corresponding parts. The overall bridge score is derived from the three major component scores, calculated based on corresponding weights. Below is the bridge technical condition assessment process flow chart. 3. Special case handling methods. Since in practice, a bridge may consist of two or composed of multiple different structural forms. When a single bridge includes an existing beam bridge, and there are arch bridges or other bridge types, the bridge can be divided into two units, and evaluate each evaluation unit one by one. Conduct grade evaluation of bridge technical condition. Then, based on the technical condition rating evaluation results, the worst evaluation unit serves as the whole bridge evaluation result. For example, the Liuyang River Bridge consists of two structural forms, respectively cable-stayed bridge and beam bridge. The cable-stayed bridge section complies with standard requirements. Use hierarchical comprehensive evaluation method for assessment, ultimately evaluated as Class 4. The beam bridge section is rated as Class 3. Combine evaluation results of cable-stayed bridges and beam bridges. The entire bridge's technical condition was ultimately evaluated as Class 4. When the technical condition ratings of the superstructure and substructure are Class 3, the bridge deck system's technical condition rating is Class 4. And the overall technical condition score of the bridge, when the calculation result is 40 is less than or equal to Dr. is less than 60. The overall technical condition of the bridge can be rated as Class 3. During the overall technical condition grade evaluation of the entire bridge, when the score of main components reaches Class 4 or 5 and affects bridge safety, can be evaluated based on the worst defect condition of bridge main components. Main components are listed in Table 3.2. In the end, I will summarize this lesson. In this lesson, we mainly explained the single control indicators for Class 5 bridges, bridge parts, components, breakdown of components, and the hierarchical comprehensive assessment process. In the evaluation process, we must maintain meticulousness, rigorous and conscientious attitude, conduct scientific evaluation strictly in accordance with specification requirements. Only then can it provide a basis for managers to formulate maintenance measures, thereby ensuring the safety of the bridge during its service life. Stabilized. After class, please consider the following questions. Among parts, components, and elements, what is the key and foundation of the entire technical condition assessment work?